This is our 5th lecture. Welcome to the first day of September, everyone. We are going to be talking about a little bit of the math behind control systems today. So I informed a few people that this is the part of the class that gets really fun. Yeah, so that's where we are. So when we have any kind of system that has an input and an output, we can really model anything. You can even apply math to pretty much anything. What we discussed last week was we talked about the fundamentals of what makes a control systems, the inputs, the outputs. We talked about feedback and the ability for a system to know whether or not it is doing a good job. What we're going to talk about today is a very simple open loop system it's just a mechanical system. So now let's say you had some kind of a stamper or something, and your stamper was, maybe you're making sheet metal parts, and it has to stamp these parts out to have little razor blades in them. Or whatever, it would cut through the metal and stamp out the parts. And this part just goes up and down repeatedly, just stamping. What we're dealing with here is, you can say, well, what's happening with this system is, you apply some amount of force downward and it stamps, and then you pull back upward. You want to be able to study maybe how the force is transmitted into the ground, how that force is provided. We no longer just treat this like a static system. Static systems don't move up and down like this. They aren't repetitively stamping. In a static system, this would just be, maybe have some force applied to it, and it would just be sitting on something. And this isn't a static system anymore, because now we have that dynamic motion. And because we have a dynamic motion, something comes into play that really wasn't in play when we studied this in statics class. Okay, this is a really simple statics problem. If this is sitting on a piece of sheet metal and you apply some force, it's a really simple problem. It's not hard at all. But it becomes a much more challenging dynamics problem. So you're just taking this thing and stamping it. This has some certain amount of mass. And that certain amount of mass means that every time it moves, it requires a certain amount of acceleration. Okay? So what you end up having on this is, if we were to draw the free body diagram, say you got your stamping force, which I'm going to call F stamp. That's what's being used to apply downward. We can say F stamp, maybe we make it be a sine function because it's going up and down. F stamp is going to be equal to, I don't know, 9 cosine of omega t, where omega is the speed and t is time. And 9 would then be just the height that it raises, or the force that's required to raise it or something. Okay. And then what we also have is, if we don't consider that it's actually touching anything on the bottom, we also have a force here that resists that force, but is the force that's equal to mass times the acceleration. Okay? When we're dealing with dynamic systems like this, your sum of your forces in the y direction are going to be equal to, well, you could say the mass times the acceleration. That's fine. And then that's equal to F stamp You could do that. This is assuming it's just floating in air, endlessly swinging. You could do something like this. Oftentimes what we do in these types of systems, though, is rather than have this be equal to ma, we make ma into a force. And we would say it's equal to negative. I'm going to go ahead and change the direction on this just so that it can be negative. Negative F XL plus F stamp, and then have that be equal to 0. Now, the only difference between this equation and what we're used to is we're treating that dynamic force, that mass times the acceleration, that it's an inertial force now. Oh man, this is the part of the class where I really love examples. You know what, Sam, you make a great example. Sam's a big guy, in case you didn't know. I mean, I like to tell people I'm a big guy, but Sam, you're pretty big. Are you a lineman?
Oh yeah.
Yeah, that's... Yeah. So let's say Sam is standing next to me right here, which I can't do because of COVID. And I'm going to push on Sam, okay? If I push on Sam, well, Sam's a big guy. He's not going to accelerate very much. The push that I'm pushing on him, which here is basically what a stamp is not going to make him go very far. He's not going to accelerate a whole lot, okay? So we can treat this as if it's a static system if we just turn that acceleration vector into a force. It's now a force that is being exerted on his center of mass that exists opposite of the direction of motion because that's where he's going. Oh, I shouldn't have changed this. Sorry. That's a negative MA. Nope. No, it's not. Dang it. Anyways, so this ends up with what we have at our usual equation, but what we're doing now is we're treating this as if it's a force. Rather than a mass times an acceleration, it's a force. And what we have here is, let's say now, with our stamper, or with any kind of system, what this is, the only forces that are being exerted on it are our external force and then our inertial force, okay? So, let's keep a list. External force. This is a force that originates from outside of the system, and it is usually used as a forcing function. Okay, so it's used to create motion or cause change in that system. Okay, that's what an external force is. We also deal with boundary conditions or boundary forces. What a boundary force is you know, if I push on Sam and Sam's in a corner, I can push as hard as I want, but Sam's never going to accelerate. The condition is that Sam cannot fly through that wall unless I can push him hard enough, which I really doubt. But that wall will always push back on him, and it will push back on him with a force necessary to prevent him from going through the wall. That boundary force exists as a displacement restriction. A lot of physical systems, when we're dealing with systems like this, they have displacement restrictions, and those displacement restrictions prevent something from traveling fast enough. In an electrical system, you will have only so many electrons. You cannot have more than that, and that serves as some kind of a boundary force because you can't pull out more electrons than that exist. That kind of a thing. But in a physical system like this, you have to deal with physical restraints caused by displacement constraints, really. Okay, these boundary forces always require some form of contact. Okay, I can't be pushing on Sam and Sam is unable to move because that wall has some kind of a force field on it that is preventing Sam from just getting any closer to it. So a boundary force does require contact. So external force, here we're only dealing with an external force because it's just floating out in air. Here we're only dealing with an inertial force. And that inertial force is the mass times the acceleration. It is a second order displacement connection. Okay, and this comes from within the system. You can only have an inertial force if it's inside of the system. If you have some kind of an inertial force that exists outside of the system, that's an external force. So this has to be now inside of the system. For a mechanical system like this, that inertial force is a mass. So for translational mechanical systems, this is mass times some acceleration. Okay, we're going to be talking about rotational systems. Rotational systems are a little bit different because now the inertial force is actually that moment of inertia that a component has. For an electrical system, that inertia is actually depending on how you look at it, if it's a current-driven system, that inertia is the capacitance of the system. And if it's a voltage-driven system, which most of ours are, then that inertial force is actually the inductance of a system. For a heat system, inertial force is how hard it is to heat up a large volume of space, basically a heat sink. For a pneumatic system, an inertial force is the amount of mass that exists in the air, or in our hydraulic system, it's the amount of mass that's in water. So really what it is for any system, an inertial force has the second order displacement relationship. That's really what defines it. Okay, so we've got these three types of forces. At this point, we're only looking at these two. The equation of motion here is you've got your F acceleration is going to be equal to your F stamp. If we go ahead and write this as a displacement relationship, this is mx double dot, where what that represents is two derivatives with time. It's just easier to write it as dots because most of our derivatives will be with time for this class. So mx double dot is equal to whatever F stamp is. We set that as, what, 9 cosine omega t. Okay, and as long as your units are correct on both sides, you should be able to solve that pretty easy. Your acceleration is going to fall very strongly in line with what your force is doing. Okay? Now let's say we apply a boundary force. Let's say that instead of maybe punching into steel, maybe this is cutting through some kind of very, very flimsy foam. Okay? Where this is constantly pushing up at some force. Okay, if we exert that force, then the free body diagram now has this force up here, which we'll call F boundary, meaning that it's touching something. And we're going to make a very dumb assumption that that is fairly constant. Or maybe it oscillates as well. Maybe it oscillates with the movement of this. So maybe what we'll say is it's also equal to 4 cosine omega t. Okay? So now we've applied a boundary condition where because it's pushing into something, there exists a force. And that force varies because this force varies. Although we still have movement in our system. It's not like nothing is moving. So kind of a dumb example. But by applying that boundary condition, when we write our equations again, that boundary condition shows up over here. Okay, what we end up with as a result is mx double dot is equal to F stamp minus F boundary. That's it. All of our external forces end up on the right side of our equation, whereas our displacement relations end up on the left. That's what we're going to do for all of these. Why? Because this is time variant. Both of these are functions of time. And this is dependent on the displacement, which the displacement is itself a function of time. It has to be a function of time because it has a double derivative in time. So here, we know x has to be equal to some function of time because it has to be able to be derived with time. Okay? And not just once, but twice. So this system itself, pretty simple. If I give you what F stamp is, and I give you what F boundary is, you can solve that no problem. You figure out what the acceleration is. You can probably do 2 integrals over this. Integral over a cosine function produces a sine function. Integral of a sine function is a negative cosine function. So you end up with, what? Negative 9 over omega squared cosine of omega t is your acceleration. There you go. Done. Ah, should have been a positive the whole time. Dang it. Anyways. So what we're dealing with this system is fairly straightforward. Just do 2 integrals. Things get a lot harder when, let's say, instead of having this type of a stamp system, let's instead get a really, 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 really lightweight stamp. So little mass that we can pretty much ignore it. And what we're going to do is, maybe it's just a system where the blades are so sharp that it doesn't really need a lot of mass to physically stamp. It just cuts because it's just that sharp. Apply a certain amount of force and it shoots. Now what we're going to do is we're going to mount these cutting blades onto a spring. Okay? And that's going to go down and it's going to press on this surface, it's going to cut into it, and we're going to apply a stamping force directly to this spring. Now we're going to assume, and this is a huge assumption, but if you have a low mass system, you can usually assume this if your math turns out okay. Assume m equals 0 for the system. It's going to make our math a lot easier. Why? Why does it make our system easier if we don't have a mass? It has something to do with this right here. What's that?
Less variables to consider.
You have less variables to consider, and you don't have an inertial force. Okay, an inertial force, this is a second order displacement relationship. So if we have no mass in our system, what it means is we're not going to have to deal with having an inertia at all, which that's nice. Okay? So as this F stamp pushes down, what we're going to be looking at here is, now this center of mass is still going to move. Right, you can't push on a spring without the center of mass of the system moving. Now we're assuming that the mass is equal to 0, so there really isn't a center of mass, but don't think too hard about that. The center of mass of the system right here is still going to move. How is it going to move? If we apply our F boundary on the bottom, what's going to happen is F stamp is going to be exerted from the top, F boundary is going to be exerted from the bottom, and it's just going to spring. Now looking at it from a system relationship, if we do all of our external forces, sum of the forces in the y direction is equal to F stamp minus F bound, that's equal to 0. We have no movement. Well, we do, but the movement doesn't change anything. You have a direct relationship between the boundary and the stamp force. You don't have an inertial force anymore. You can figure out how much this compression is based on, you know, that F stamp is compressing the spring, and that spring is going to be equal to F spring. And your spring force, anybody remember the relationship for spring? Times X, yes. It's equal to, well, I'm just going to put positive Kx. Okay? So the stamping force is directly related to the displacement of that spring now. And that as that spring compresses, it is exactly and directly transmitting exactly what F stamp is to the ground, which is why F boundary is equal to F stamp at all times. Okay? This is true because the spring sends that relationship constantly. So spring forces are a little bit different than inertial forces. Okay? This is what happens here is as F stamp pushes on here, you're going to end up storing energy inside of the spring. Anytime you compress a spring, you're storing energy there. Okay? In an inertial force, energy is stored in the movement of the mass. Kinetic energy is energy. Motion is energy. Accelerating is a change in that kinetic energy of the system. So an inertial force is a change in the kinetic energy for a mechanical system. A spring force is a change in the potential energy for the system. Okay? Does that make sense? Do I need to say it again? If we're just looking at energies here, there is a huge difference between these two types of systems because in this one, the energy exists kinetically. In this one, the energy exists as potential energy. Both of those energies you can receive energy back out of. If we're only looking at the energy of the stamper, 100% of this energy is being transmitted directly into the ground or directly into whatever system is being stamped. Okay? 100%. In this one, 100% of the force is being transmitted, but you're also going to have a very weird relationship between the boundary and the stamper where some of that energy is actually absorbed with the motion of the system. you don't quite get all of the energy of the stamping. You get, and you don't, and that showed in the force relationship where not all of the force was being exerted in the boundary, but I gave that to you, so it's kind of cheating. So what we have is now a spring force. Let's see if I can, yep, I can right over here. Okay, we're going to call this just a spring or a capacitive force. And the idea behind this kind of force stores energy, but the relationship is linear. Here, it's a linear relationship with x, so the more force is applied, the larger x becomes. K is that linear spring constant. Okay, keyword here is potential energy. In a translational mechanical system, this capacitive force is K times X. Some linear relationship multiplied by the distance that it compresses. Okay? We can treat materials like a spring. Concrete compresses. Every time you walk on the floor compresses. I'm a heavy guy. I can feel the carpet compressing underneath me. That material is behaving as a spring. It's actually absorbing energy. And it releases that energy when I stand back up, when I pull my foot back off of it. Materials behave like springs. Unfortunately, materials are also viscoelastic, which means they also have energy dissipation in them. If you pull on a material rapidly, it will exert a lot of heat. So, I'm going to go ahead and I'm going to say, all right, let's build a stamper system, but let's give it the works. Let's make this a more complex stamper system. This is now something that's going to come down, stamp. It's going to use the spring force up here. So it's mounted to this, and the spring pushes down on the stamper. The stamper has some mass. We'll say that the stamper itself, the center of mass is down here. We'll assume that the spring itself has no weight. And then what we're going to do is we're also going to apply some kind of a damper. Okay? And this is a damper. This is a spring. And this is a stamping mass. Okay, because again, we're just dealing with some kind of a mechanical stamper that comes down, smashes into a piece of metal, pulls back up. Okay? What the damper does is the damper, it's kind of, it represents the friction in the system. We can't have some kind of a stamping system that exists absent of friction. So if I were to go over here, the damping force it's a derivative relationship. Where force is applied to a system as energy is converted to heat. Okay? This is a damper in a mechanical system. So it's just friction. So in a translational mechanical system, we're going to consider this to be viscous damping because the relationships for other types of friction tend to be uglier with math. So no, this does not represent all kinds of friction. And yes, most of the mathematical relationships that you've learned for friction right now no longer apply. Here, you recognize that a lot of damping, if you exert a friction force, your kinetic friction force is equal to mu times the normal force, right? This is what you're used to. This is not what we're talking about in this class. This is a simplification of a friction condition that occurs between derived surfaces. What we're going to assume here is a damping force is viscous. Okay? This is viscous friction, represented by C x dot, where C is the coefficient of viscous damping and x dot is the velocity of that component. Okay? In viscous damping, anytime you have fluids involved, the velocity of that fluid, you increase the velocity of the two components relative to each other. It requires a higher shear stress inside of that material in order to be able to handle that variance in velocity. So in viscous friction, it is very much related here. This is dry friction. This could be considered almost like a spring force, or almost like a constant force even. We're not going to throw it into this class because it does make things more complicated, this dry friction. So for the sake of this class, we're going to be representing friction as viscous friction. Viscous meaning it's got fluids involved in it, and it has this relationship. So if I were to talk about all of the forces that are being exerted on this mass right here at any time, say we've got this spring that's connecting to some kind of a ceiling up here, we got a damper that's connecting to a ceiling, and what we're going to do is we're going to apply a stamping force right here, exerted downward. It's going to be pushing this thing down into some kind of a surface. For right now, let's assume that there is no surface. It's not just pushing into something. Let's assume it's just floating in free air, bouncing up and down. Okay? If we do our sum of the forces in the y direction, what that is equal to is you got your spring force. This is Fs. You got your damper force, Fd. You have your stamping force. And then you've got your inertial force, Fma. So Fma plus Fs plus Fd plus F stamp, and that's equal to 0. Now again, we included Ma as a force in here. That's this thing. This is force. That is the force that's caused by inertial force, mass times acceleration. That's not F times Ma, it's F subscript Ma, just like this is F subscript S, F subscript D. So what you have here is this is going to equal 0 because usually we have Ma on the other side. But we're going to be playing around with this because we have multiple displacement relationships that are going on simultaneously. All right? We have this formula here. This is equal to Fs. Okay? This is equal to the force caused by the damper. we have this is equal to FMA. Okay? So we can bring each one of these in where MA is the acceleration is 2 x's. So what we have is mass times our acceleration plus force, the spring constant times the displacement of that spring, plus the damping coefficient times the velocity of the damper, plus whatever that damping force is equal to 0. We assume all the force vectors go in the same direction because heck, why not? Now we'll go ahead and bring this to the other side. This is a time variant independent external force. This does not depend on the displacement of the system. It has no relationship with the displacement of the system. This force exists in isolation. It's going to exist no matter what the system is. That is, whatever the system is that is actually friggin' pounding this thing, it doesn't care about what this system consists of. It will always produce the same force regardless of what M, K, and C are. All right, so we take our external forces and our boundary forces and we put them on the other side because they are time variant, not displacement variant. Okay, here, this is a displacement variant, it's got an x. This is displacement variant, also got an x. This is displacement variant because it's also got an x. Now, this is an x with 2 derivatives, x with no derivative, x with 1 derivative. So we'll just clean this equation up, take all of our displacement relationships, put it on one side, put all of our time relationships and put it on the other. Okay, time relationships are these 2, displacement relationships are these 3. Well, you get mx double dot plus cx dot plus kx, yes, I just switched those around, is equal to negative f stamp, which is some time varying equation. Okay? This is the equation of motion for this system. If you can figure out what f stamp is, you can use differential equations to figure out what x is. And from that, you get a time variant function for x. You can figure out what the velocity is. And once you know what the velocity is, you get a time varying function for velocity. You can figure out what the acceleration is at all times. You can then turn around and plot. Here's what the acceleration is. Here's what the velocity is. Here's what the displacement is. So for our f stamp is equal to, I don't know, 10 cosine of t. We have this. This is called our forcing function. If you remember this from electronics, we're right back there again. That's our forcing function. This is what is causing change to happen in the system. If this is equal to 0, this system will eventually come to rest. Not right away. Okay, everything has some inertia. If this is already moving and then suddenly the stamper turns off, this is still going to be moving. There's still going to be some acceleration. There's still going to be some velocity. Just shutting off that stamping force does not stop the movement. The system continues to move afterwards. Okay? If you have ever taken, how many of you have used a circular saw? Most everybody, okay? When you turn on a circular saw and you let it run for a little bit and then you pull your finger off the trigger, does the blade immediately stop? What causes the blade to stop? Eventually, it's friction. All of that has to go somewhere. All the energy that's contained in that rotation of the blade eventually has to go somewhere, and the only place it really can go is friction. What we talked about in electronics is if you had a system that only has a capacitor and an inductor in it and has no resistor, the energy is going to bounce between those two systems forever. You'll have trapped energy forever because it has no way of leaving the system. The only way energy can leave the system is through friction. It's through heat. Heat is the universal way that we take energy and have it leave a system. So in some ways it's necessary. Without this force here, if we take F stamp out, this thing will continue to accelerate and the spring will just continue to elongate and shorten based on how it's accelerating. It forms a harmonic system that just constantly bounces forever. That's not really necessary. That's not even desirable. You don't want it, you don't want this thing to continue to stamp after the stamping force gets shut off because it still has energy in the system that's trapped there. So the damper does play a critical role in this because it serves as the ability for energy to leave the system. Okay? Yes, everything I gave you here today was about forces. But forces, when you consider displacement, produce energy. Anytime you have energy, you have power. So we're talking about forces and we're talking about power at the same time. Everything intermeshes. When I said you could have 1 million inputs to a system, well, you have stuff like this where not only does this system depend on the forces to form the acceleration, it also depends on the energies in the system. It depends on the energies outside of the system. You can be measuring the energies outside of the system. You can be measuring the energies inside of the system. This only takes into account the forces from viscous damping, which means fluid friction. Doesn't take into account static friction, doesn't take into account the dynamic force of friction that's caused by dry contact. This doesn't take into account any of the variances that's caused by components heating up. As the components heat up, there are changes in size, there are changes in values of this. You do have some, when it gets bigger, it does impact the overall size of the system. Minutely, but it does. You could write a term into this equation about how the heating up causes a force. You could talk about any condensation that occurs as a result of this process. You could talk about the pneumatic force, the fact that this is being moved up and down in a room filled with air. Every time it moves up, air has to get out of the way. Every time it moves down, air has to get out of the way. There is a pneumatic force associated with this. There's so many different forces that we could put in here. There are going to be magnetic forces. There's gravitational forces for these two components. There's an infinite number of inputs that we could put into the system. But what we're caring about here, what we're primarily caring about is this displacement vector. And the whole reason why we wrote this formula is to understand how the system moves. Okay? In a mechanical translational system, we care primarily about how the system moves. All right, any questions on this? All right, let's go ahead and cover another example. We've talked a lot about this class about how a suspension system can be used as a control system. Let's go ahead and look at just the math behind that. Now, again, we're not solving these formulas. I'm not requiring you to solve these formulas for a few weeks. So, you have a little bit of a break, but I need you to understand how to derive them. Okay? This one's fairly simple. But I'm going to ask you, how to build the system of what this looks like. So here we got a tire, and connected to that tire is a wheel hub, the axle. And that axle is connected to the vehicle by a spring, and sometimes you'll have a pneumatic damper. Pneumatic is a fluid damper, which we can treat as a viscous damper system, and that is connected to the vehicle. Okay, this is just a single wheel model. This is a common way of drawing a suspension system. It's fairly simple. It's extremely simple. But everybody has one of these in their car. So the question is, how do we take this and model it for when this vehicle is riding and all of a sudden it hits a bump? How do we handle that? Okay, question. We have three types of forces that exist inside of a system. What are they? But just erase them.
External force, boundary force.
That exist inside of a system. The boundary force and the external force exist outside of a system. Inertial, damping, and spring forces or capacitive forces. Okay? What's the difference between an inertial force and a capacitive force? Linear force is, the capacitive force is linear, whereas the inertial force is a second order system. Okay? All right, I'm going to take this tire and I'm going to drive it over this bump. Now, the moment that this tire hits that bump, this vehicle is traveling at a fast enough speed that we can assume that the car body does not move. Okay, at the very beginning. Because this does have a very high inertia. Some cars are anywhere between 2,000 to 5,000 pounds. You can get trucks that are 8,000 pounds. You can get single unit trucks that are 10,000 pounds to 40,000 pound. You can get just giant trucks. In any case, 2,000 pounds still for this mass, even if it's only 500, because we're only looking at one tire out of a 2,000 pound car. 500 pounds is still a lot of mass to move by a very sudden bump in the roadway. So how is this force transmitted? Well, if I were to draw this again with now this tire over here, what does this look like from the side? Well, you've got your car body, which doesn't move. You may have some compression of the spring, although that's kind of unlikely because it would also require some compression of the damper. And the damper,
But the damper doesn't act until a certain amount of spring acts, right? Or are we assuming they're acting at the same time?
we're going to assume that they act at the same time for this. It is a very simple model. Okay, so as the tire drives over that bump, this is what it looks like. Okay. Your tires deform all the time. In fact, that's what tires are intended to do. They're built out of rubber so that they can deform with the roadway. They pop back into place. That's what they do. In a very, very simple vehicle model, is there going to be, well, we can assume that any viscous damping that is caused by the tire running over this is pretty much negligible. Yes, it will cause the air in the tire to move a little bit, but it's really not going to cause the air in the tire to move a ton. We're going to assume that. Okay? We're also going to assume that this tire is pretty lightweight compared to the vehicle. So you can assume that the tire itself has no mass. In a very, very simple suspension model, what you have is this is the mass. Here is a spring. Here's the damper. We're going to mount it to a massless platform. That massless platform is the center axle of this vehicle. And then this is going to be connected to the ground with a spring. This spring represents the tire. Why are we using a spring? Right, because the force that's being exerted upward by the tire, we're going to assume that it has a linear relationship with what it's running over. It's just an assumption. This is, again, it's a model. It's not perfect. If you were to try to perfectly model this, you would have to take into consideration the mass of the tire. You would have to take into consideration the viscous damping of the tire. But in a very simple model like this, we're just going to treat it like this. What is the forcing function here? The what? It's the bump. Okay? The bump causes compression of this spring. It's a displacement relationship. Okay? It's not an actual force. It is a force displacement. You can't run over this bump and be like, well, I have a force limitation, so I'm only going to run over part of this bump. The bump's got to look like this. Like, no, it's not going to do that. A tire is not going to suddenly go into the road. It has to go over the road. That's the displacement relationship. So what we have here is you are going to have a forcing function that is based on the compression of this spring.
Is that function equal to the summation of the forces on the top?
Well, let's go ahead and assume that the relationship looks like this, and that the displacement is maybe we're running over a 4-inch block or something, certain size. It's causing this to compress for maybe half a second or so. What's going to happen is your force relationship through this spring. So if this is FS1, because this will be our spring 1, this will be our spring 2, this is our damper, and this is our mass. Our FS1 is 0, or net 0, because it's riding on the ground. There's upward, downward. We're going to assume that it's 0 before this. But then it jumps all of a sudden, and it tapers downward. And then eventually it releases. Okay? This is what the force in the spring tire looks like. This initial force right here is going to be equal to the height of this block multiplied by the spring constant of the tire. So if this is, I don't know, I'll use the letter A. If we're looking at the height A, or you know what, H is better than A, sorry. Okay, this is equal to K1 times H. Why does that force decrease?
That's the spring returning, or the tire returning to its shape.
It is this tire returning to its shape, yes. And in order for it to return to its shape, as it is traveling over this, what has to happen to the suspension? The suspension itself is compressing. So the tire is returning to its natural shape by equalizing some of the force that's here. At the very beginning, all of the force of hitting that bump is stored in the tire. Every bit of it. None of it is transmitted here. Okay? Why is that? Because this damper cannot allow a vehicle to suddenly reach an infinite velocity. It can't. The relationship, the force being exerted by this damper, Fd is equal to Cx dot. If the velocity suddenly reaches infinity, because the vehicle suspension moves upward, suddenly, then what this is Fd is equal to infinity too. Your damper prevents your axle from moving instantaneously. You cannot have an infinite velocity, which means your displacement relationship, so we'll talk about displacement of the axle. Okay? If this is time t1 where you hit the bump, and this is time t1, your displacement of the axle cannot change from right here before t1 to right here after t1. Your displacement of your axle cannot change suddenly because this right here cannot have an infinite force value. You can't have a step function. You can't have the displacement of the axle suddenly do this. If it did that, this force would not be K1H. But because we have that damper there, because we cannot have an infinite velocity after hitting this bump, it has to be more gradual. It has to be much more gradual. What you'll see is this has to be a continuous function. It ends up swooping up really sharply. Yes, heck yes, that's a very strong line. But this is still a derivative, and it is still a non-infinite velocity. Does that make sense? So your axle, yes, it does accelerate after the impact, but it does not immediately jump. For that reason, all of the force has to be taken here through the spring because the top of the spring isn't moving. Only the bottom part of the spring is moving. But as the bottom part of the spring moves upward, as your tire deforms and starts pushing up on this axle, your damper and your spring will also begin to compress. The tire will restore, which is what we're seeing here, and then eventually it goes off the bump and it fully restores, and then the tire kind of goes back down into the ground. In a good suspension, your displacement of your axle will not do this. You're not going to suddenly fly up in the air. A bad suspension, you fly right up in the air. Okay, if you have no springs, or if your springs are shot, hitting a bump causes those springs to compress, and then your vehicle launches upward. Which if you've ever been in an old truck and had that happen, really fun, but will make you wet your pants. I don't speak from experience or anything. No, I've never peed myself driving down a country road. I just need to stop talking. Okay, we still have 15 minutes left. So this is a fairly simple model. Now, the behavior of this system post this, it's not intuitive right away. We're not going to be able to sit here and say, okay, I know exactly what the system is going to do. We can't know. We can say that, if we use our mathematical relationships, we can figure out what that is going to be. Okay, if you're hitting a bump this big, you eventually want your vehicle to restore. You want the car to move upward at some point, maybe. If the bump is only this wide, your perfect suspension will have your vehicle never move up. If your vehicle never moves upward, do you feel the bump inside the car? You're standing on the mass, or you're sitting in the mass. If this mass never moves, do you ever feel the bump? Is that a good suspension or a bad suspension? If you never feel this bump, that's a good suspension. Great. It's exactly what it's supposed to do. Vehicle mass, maybe it moves, but maybe it moves so gradually that you hardly feel it. It's good suspension. Okay? Bad suspension. This isn't a bump. This is a curb, and that ground is flat afterwards. You never move upward. Is that good suspension or a bad suspension? That's bad because it means the next time you hit a bump and the next time, pretty soon your vehicle is going to be running into it. Your suspension just keeps compressing until your car runs into a mountain. Okay? So you do want the mass to move at some point. And you want it to move substantially at some point, particularly when you're going upstairs. But you do not want it to move upward for a very tiny bump. That is the difficulty that we have with suspension. We can design a system such that this mass doesn't move. We can design that. We're all smart enough. I'm sure you guys could figure that out. Put enough time in it. You can figure out a suspension that's super comfortable. But coming up with a suspension that also allows your vehicle to drive over varying heights of terrain would be much more challenging. It is the year 2020. We are still designing vehicle suspensions. Nobody has created the perfect suspension system. We've had vehicle suspensions for over 100 years. Model T had a suspension. And we are still designing them. Okay? When I was a young engineer, I thought that all the engineering problems were solved. I had no idea people were still designing suspensions, which I thought were a given. I have people brighter than me right now who are building suspensions who still are not building the final version of their suspension systems. And even when they're done, their suspension systems probably won't even be perfect. We still have time in our lives to design a better suspension system, and this is fundamental to a vehicle. Because this math is ugly. Okay? So if I write the math equation for this, which is what I started to do before I walked over here. This gets a little bit more challenging. Okay, in the last system we had one displacement. In this system, we now have two displacements. You have the displacement of the axle, and you have the displacement of the vehicle. Okay? And what you want for your vehicle is you may want it to go up a little bit and come back down, but you want it to be very gradual. High impact, when you suddenly bounce up and down, it creates an immense amount of acceleration on you as a person, which is extremely uncomfortable. Lower accelerations make people comfortable. If your vehicle very gradually moves upward because it hits a bump, and very gradually moves back downward, that's much more comfortable than having a sudden bump like this. Okay? It is the job of your suspension to reduce those accelerations. This actually ends up being a filter. It filters out high frequency impacts, but it allows low frequency impacts to occur. Low frequency being like when you're hitting an incline and you're going up. High frequency when you're hitting a bump. Okay? So your suspension does act as a filter, and it prevents you from feeling this, but you do this instead, which even then, this is much smaller than that and much more gradual. That's comfortable. This is not comfortable. If you were sitting right on your tire, or if you've ever ridden in a trailer that does not have suspension, anybody done that? I have too. It's a ride. You kind of bounce all over. That's fun. Boy, after a while though, you get out and you kiss the ground. But that's what it is this is your displacement, not this. That's the difference between these two. This is much more comfortable than this, but this is still more comfortable. So in the math, if we're taking this as our system, we got S1, S2, D, and M. Okay? If we look at the axle, we're going to draw a free body diagram of the axle. Okay? You have FS1 pointing upward. You have FS2 pointing downward. You have FD also pointing downward. Exert on top. I mean, FD, viscous damping, can exert in both locations. So it could be pointing upward, I don't know. But at this point, I'm just picking this as the input and the output. Okay? FS1 itself is a relationship between the ground, which we'll call 0, and the axle, which we will call x1. So the height of the axle is equal to x1. Any questions so far? Okay, we're only looking at the axle right now. Okay, what is, if we look at the vehicle body, the mass, what kind of forces does it experience? What is a free body diagram of that mass? Okay, so you got FS2 and you got FD. And we also got one more force that we're going to label. It's the inertial force. Okay, yes, you have a gravitational force that's weighing down on this. Yes, that's correct. But you also have your m times your acceleration, which is x2, which I should just write it as fmx, fma 2. Okay, the height of the vehicle is at x2. Okay, height of ground is equal to 0. So the height of the vehicle off of the ground is equal to x2 minus 0, right? So distance from axle to ground, and then we're going to assume that 0, like when you hit the bump, like the bump exists above 0. Okay, we'll just assume that. Or we could even say that maybe the bump is 0 now. You can do whatever you want with math. But so the distance from the axle to the ground is x1 minus 0. Okay? Distance from the vehicle to the ground. What do you think the equation is here? x2 minus 0. That's pretty simple. Okay. Distance from axle to top of bump. Okay. Here, we're going to assume that the bump has height h. So what is the distance between the vehicle and the top of the bump? Well, the axle and the top of the bump. It's x1 minus h. I feel like I'm asking dumb questions here, but that's all it is. We know what that distance is. Okay? And then the distance from the vehicle to the axle what is that equation? Well, from vehicle to axle. Yep. Yep, that's it. Yay! Now, how this distance changes is the velocity difference between the axle and the vehicle. Why is that important? What's that?
So we know the original position.
Yeah, we'll know what this original distance is from before when it hit the system. We'll know what that is if we know what this starts as. Now, as we do the math here, the math is going to very strongly depend on these 4 variables. This is the reason why I had you explicitly write this out. Because we're dealing with 2 different systems that move relative to each other, we now have to take into consideration, is our system on the bump right now? If it's not on the bump, it's on the ground. Okay? That spring distance is this when it's not on the bump. That spring distance is this when it is on the bump. And it is a very sudden transition. The way that we drew our bump is that h is just all of a sudden, bam, it's there. It's called the singularity function. It just suddenly exists. Okay? And the reason why our spring in our tire suddenly exerts a force is because at equilibrium, driving across the roadway, Fs is equal to kx1 minus 0. Oops. All right, this is the static force that's holding the tire, that's pushing up on the tire, that is required to support the vehicle. So, in equilibrium, before hitting bump, this is the case. And x1 is likely a constant value here. Okay, before hitting the bump, we're going to assume that there's no bumps in the roadway. The vehicle's not moving. Everything's in equilibrium. This is a measurable value. We can figure out what the compression is needed in order to support this. Now, Fs1 has to carry the full weight of the vehicle. If we look at this system and we do a static analysis on it, I'm almost out of time. If we do a static analysis on this system, I'm going to go ahead and erase this. When the vehicle is in equilibrium, before it has hit the bump, while everything is, there's no relative velocity between the axle and the vehicle, meaning the distance x2 to x1 is constant. The distance between the axle and the ground is constant. Everything is in equilibrium. Prior to the bump, your free body diagram looks like this. Okay, you have two forces. Those two forces exist outside of the system. Fn is equal to Fg. Now, the reason why I said that when it's in equilibrium, there's no velocities, there's no changing distance, this is a constant, also means there's no acceleration. There's no acceleration, we know these two forces are equal. When there is acceleration, there's no guarantee anymore. So, prior to hitting the bump, Fs is equal to this. If we only look at Fs, just pulling out this piece right here, okay, the axle, you got Fs pointing upward, you got Fs pointing downward, you got Fn pointing into this, and we'll say this is the bottom of the tire, it's Fs pointing downward. Fs1 is going to be equal to that normal force. That spring force that's being carried by the tire is equal to the amount of force that's needed to hold the vehicle up. Huh?
Fn equal to Fs1, Fs1 equal to Fs2, and Fp equal to Fq.
Yes. Yes. If you continue to go through here, because there's no relative velocity here, the damper's carrying no force. All of the force is being carried in the spring. So Fs1 equals Fs2, which equals Fg, which equals Fn. They're all equal to each other. Good point.
Our equation become more complex if we consider once it travels a certain distance, then the mass would move.
Yes.
It would become more complex.
Yes, because what happens there is you have to exert a boundary force condition, where as soon as it goes upward a certain amount, then the force value that is transmitted increases exponentially. That is very, very, it does make the model harder. As long as you're dealing with low distances, that's fine. But that's why suspension is so challenging to model. That's why we're still designing it. So we know this is equal to Fg, which is equal to Fn. You can figure out what all of these values are. If you know what the K value is, which you should know for your tire, you can figure out what this height is based on what the gravity force is. Okay? And you can figure out what the distance x2 to x1 is based on gravity and using K2. You can figure that out before the bump. You can know these values. As soon as the vehicle hits though, we'll talk about that next time. Okay, you have homework due Thursday. There's a quiz. There's a design problem that looks remarkably like a problem that I gave you in class last week, if you watched the lecture. You also have a reading assignment due this week. I will be assigning and having homeworks due on Thursdays every week this semester. 2 weeks from now, I'm going to be giving you your project, and you're going to be having, well, next week I'm going to be giving you your project, and then you're going to have to hand in pieces of your project as part of your work for the class. We'll talk about that next week. But otherwise, have a good rest of your Tuesday, and I will see you on Thursday. If you have any questions on the homework, feel free to email me. Matt, I did post that link. I apologize I didn't have that. Thanks for catching that.